I'm done with the solver one. If you want any extra quantities to have in your results, just go to data file quantities and have. So as I wanted skin friction coefficient, so I went to data file quantities and just kept skin friction coefficient. So before closing it, I just want to run for more 200 iterations. So in data file quantities, the things which you have on right side will be displayed, that you can display them on your results. The things which are on left side are the extra quantities which you want to import them in your results or which you want them in your results. So after everything is done, just close your solver. And now our main aim is to do CFD post processing. So post processing is what to say, a very huge amount of development work which has taken recently. So many of the you might like post processing because you'll have many different colors and visualizations. So to have the safety post processing, so click on the results and then drag it to project schematic and then transfer your solution data to results. So now go and edit on your results. So most likely the post processor has to have a very better post processing. You need to have a very good workstation laptop or maybe a workstation PC. So most of them, these packages will have domain geometry and grid display, vector plots, line and shaded contour plots, 2D and 3D surface plots, particle tracking, view manipulation, which is translation, rotational scaling, etc. So color post script view. These all you'll have in your post processor. So most recently facilities may be also include animation for dynamic display and animation for your fluid flow. So how your fluid is varying. So these are the advantages of having post processor. Without doing an experiment physically, you can visualize the particle tracking. So particle tracking, most likely you can implement it for uh, combustion engines or maybe IC engines, etc. So CFD post processing is a major thing. Everyone just like the CFD post processing because it has many colors and it has many contours. But then you should not look onto the colors or contours. You have to look, but then you need to understand what the color or contour shows. So this is where the all the engineers or maybe students does wrong. So to have a better idea, you need to know what the graphical representation mean physically. So then only there will be validation of your CFD analysis, or maybe you will have a better understanding of the CFD analysis or flow analysis of what you want to do. So most of you guys must concentrate on the post processing, because here you'll have the results, and even the latest softwares like answers are providing to export your results. So even you can visualize them in other other applications which are available in your PC. So okay, now let us see the results. The first result I want to see is pressure contour. So then just click on the contour, and then in the locations keep symmetry 1, and then the variable will be pressure, and you see the range is global. So just want to zoom in near the inlet. You there only you can see a very huge amount of pressure, but then it is decreasing as it goes to near the further outlet, because here we gave 0 pascals, which is gauge pressure, which means there is 1 atmosphere and the outlet is exposed to the atmosphere. This is what physically it means. You must know after doing the analysis. And the second contour I want to to know is vector, so velocity contour. So and then my variable will be velocity and location will be symmetry 1. So before doing that, uncheck your pressure contour. So you can see the velocity magnitude as a contour which displays with different colors. So but then you need to know that is how the velocity is developing inside a pipe as a laminar flow. So you must check whether it is fully developed or not, at which distance it is fully developed, and then you must visualize. So I'm increasing the number of contours to see the fineness of the display, graphical display which I have. As you zoom in very much, you can see the contours very fine and finer. So now same thing I want to do with pressure. So most likely you will have the more pressure near the inlet. As you zoom in, you can just see how the pressure is varying and you are visualizing it. So but then you need to know. So I wanted to see skin friction coefficient in the symmetry 1, and my variable will be skin friction coefficient. So applying it to symmetry 1, which physically doesn't represent anything, because you'll have skin friction coefficient near the walls. So I just want to keep the location to the wall. So near the wall you can't see anything because our analysis is most likely 2D. So if you want to see, you can just scale it and view it. But then I don't want to see, but I want to export that data and then visualize it in other application. So for that you need to define a location like line. So okay, I am inserting location line 1, where even I can see the velocity profile and any variable which I want at that particular line. So I will export the data. So I want to keep the point to 0.2 of y2 for the line and 0.04 for x. So you can see the line with which is displayed in yellow color. Sorry for this one. Here I should have a 0. If it is 0.2 and 0.2, it represents a point on the uh, upper line. So even I have to change my x1 to 0.004, then you can see a straight line. So what I want to do is now export the velocity data near my line, which are evaluated by the solver of ANSYS. So here you can just give your file name. So after giving your file name, you can see the locations there, and in the locations make it as line 1, and then you have to select a variable. Down you can see, and then the select variables, I want the velocity. So just click on the velocity and then OK. You can see the file is exported. So after the file is exported, I wanted to open my file location. So initially you can see while saving your file, you can see the location. So my file location, I think it is in documents. Yeah. So in documents, where I have found it, laminar. Oh yeah, laminar pipe flows. So here you can see the velocity profile. So here you can see your data is exported in CSV. So I don't need Z because the Z is 0. Ours is a 2D analysis. And then I don't want X also because our velocity is varying with respect to Y. So I just want to plot a graph between these both. So for doing that in Excel sheet, so you need to go to scatter and select the data. And my okay, go to select data and then go for edit, and then add the X. No, I want X to be velocity and Y to be my. Also, there is some error, so I don't want to delete and add a new data. So X values, I want the Y velocity, and the Y I want to be the Y value, which is in meters. So select the data accordingly. So then you can see, you can plot a velocity profile at which the X is 0.004, and you can see the velocity profile is like this at 0.004 meters. So you can do the same thing at different locations and see how the velocity profile is varying, and at you can know at which length your the flow is fully developed. So I've done this before only, so I'm showing you the results or the plot which I've got. So this is my velocity profile. I can see that the velocity is fully developed at 2.5 meters. So the fully developed flow of my pipe is at 2.5 meters. So one more thing, even you can include the pressure and plot your pressure velocity, pressure profiles. So I wanted to show you guys the velocity vectors, which will show the magnitude and direction. Yes, this is what I wanted to show. So the velocity contour gives you just only the magnitude, but the velocity vectors will give you the magnitude and the direction both. That's it. Thank you guys.